Today we're going to look at the ambiguous case of the sine law, and then we're going to go ahead and solve problems. It is really important today that you actually construct or try to construct the triangles that I'm going to give you so you can see how obvious the answer is. Today the question is going to be, how many triangles can you draw? And the answer is 0, 1, or 2. And if they're 0, that's not a problem because we can't solve a non-triangle question with trigonometry. If the answer is 1, well, that's what we've been doing over the unit before and this unit. But if the answer is 2, that's something a little bit new. We need to know there's 2. We really need to know why there's 2. And then we need to go ahead and solve 2 triangle problems. And the easiest way to figure out there's 2 triangles is to simply draw a picture. So here's a little investigation I'd like you to do. And again, I'd like you to read through it. And then, so I'd like you to read through it, draw the picture, and see what you see. So again, pause the video, go ahead, draw this little picture in the space given, and see what you see. You're going to need a protractor. Okay, so here's what you should have drawn. Again, I can't use a ruler on this, so I'm going to have to draw it by hand. But this is supposed to be the flat part of the roof, and this is supposed to be the 5.5 centimeters. Again, draw it accurately. So here's our 5.5 centimeters. And here's the angle of 40 degrees. And here is that vertical right there, which makes a right triangle. So the first thing I want us to be able to notice is, depending on this side here, and I'm just going to call it H, H for height of the triangle. If we wanted to calculate the height of any triangle formed in this story, all we'd have to do is our grade 10 trigonometry. And in this relationship, we're going to use the sine ratio is equal to h over 5.5. Then h is equal to 5.5 times the sine of 40. And when I get out my calculator and I punch in 5.5 sine of 40, we get 3.535. So let's just use 3.5. Okay, so what that says right there is if the height of this triangle is about 3.5, 3.535, then we get one triangle. Now remember what I said, the key idea today is we need to figure out how many triangles we have. So the 2 centimeter side in the story above about the solar panel on the roof, obviously it is too short. So if the supporting brace, the supporting bracket is 2 centimeters long, then we can't make a triangle. So again, pictorially, it would kind of look like that. That's obviously not making a triangle. So if the side was 3 centimeters long, again, 3 centimeters is still shorter than 3.5, so we won't be able to make a triangle. Okay, so then the question becomes, what happens if the length of the side is 4? So again, what I'd like you to go back to this picture right here and think about, well, obviously if it's 4, it is longer than 3.5, so that brace would go into the roof. But again, that's impossible. We want to make a triangle. Now, nobody said we'd have to make a right triangle. So imagine what you could do if that was a physical stick. Well, what you could do is you could swing this out this way, so it looked like that. And there we would have a triangle. It wouldn't be a right triangle, but in grade 11, we don't care. So in this one right here, well, there's one, but what I want you to recognize as well is you could have also swung it this way. And if you swung it this way, I'll just do a dashed line, but remember that's supposed to represent a side of a triangle. Well, if I swing it this way, then I want you to see you have a different kind of triangle. The first triangle we talked about was an acute triangle. This one is obviously an obtuse triangle. So with a 4 centimeter piece, it ends up we can have 2 triangles. Now, what about a 5? So again, I'm just going to extend this a little bit. So now I've added a centimeter. And I want you to see the same thing. We can swing it this way. We can swing it this way. And we end up having one obtuse triangle and one acute triangle. So with a 5 centimeter, we can make 2 triangles. And finally, what about a 6? Now there's going to be a convention we're going to use. But if we had a 6, again, I'll just imagine I had it a centimeter. If you swung this one this way, it would actually end up on the other side. So we're going to say the triangles always have to be to the right of the 40 degrees. So that piece goes past our starting point, if you want to think about it that way. So that's not going to count as a triangle, so the only way we can go in this one is to the right. So here's an example of where we made the other side a little bit too long, and we can only make 2 triangles. So I want you to think about that for a sec. How do you get no triangles? Well, in order to get no triangles, what you should notice is that side that we're moving around is less than 3.5. And again, if it's less than the height of a right triangle, it's impossible to make a triangle. Well, what do you notice about these 2 things right here? Well, side length 4 and side length 5, the side is greater than 3.5. So 4 is bigger than 3.5 and 5 is bigger than 3.5. But it's also less than the other side, 5.5. And then finally, how do you only get 1 triangle? Well, the side is greater than 5.5. And as you do a few examples, I want you to always think about this. We're always thinking about what information we know and what has to happen. The other really important thing is draw the picture accurately as we can. So again, the situation we looked at is a case where the given 2 sides and an angle opposite them, a matching set. Again, you should think sine law. That's this SSA, side-side angle. And a situation like this leads to 2 possible triangles, and this is what we mean by the ambiguous. Ambiguous means not clear, not straightforward, a little bit confusing. But it leads to this question: what part of the sine law leads to 2 possible cases? Well, I'm going to use my own language, but here's what it turns out to be. When we have an obtuse angle we get, and here's my word, we get the hidden angle. And the hidden angle is when I swung the side of the triangle to the other side. So it's going to be really important, as I said, drawing a picture. So there's a couple of typos here. They're fixed in your notes, but I'm going to fix mine right now just so you can do this accurately. I actually want you to draw this picture. So go ahead with a ruler and a protractor, always start off like this. Always have your horizontal, and this is going to be angle A, and then you're going to go up. For example, you're going to go up, in this case, 75 degrees. And this side, calling it side B is always going to be that dimension. And side A, well, little a is opposite big A. Little a is always going to be that side of the triangle right there. So again, follow this convention. Angle A at the point, little b is that yellow highlighted line that you're going to draw at 75 degrees, and little a is the side opposite. And I want to know, can you draw a triangle? So pause the video, go ahead and do that. Again, this is not to scale, I can't use a ruler, but I'm going to go ahead and I'll just label it. So here's angle A, and it's 75 degrees. And here's little b, it's 6. And when I draw my little a equals 2, what we should see is we get no triangle. And again, if we look back to this idea right here, hey, look at that. My side is less than something, and it won't work. So in this one right here, it's physically impossible to draw a triangle. Okay, next one you should have drawn. So in this one here, we have 50 degrees. Again, I'm just going to eyeball it. Oops. Let me redraw that a little bit better. Okay, so this one right here, if I draw 50 degrees and I draw this little b is equal to 2, when I actually make a triangle, I get my ruler out. The only triangle I can make where the other side is equal to 5 is that one right there. And I get one triangle. And again, I could actually swing this one on the other side, but we said we have to keep to the right-hand side all the time. So again, there's physically only one triangle we can draw. Okay, let's look at this one. Angle A is 115 degrees, so 115 degrees looks about like that. So here's my angle A, 115. And here's my little b, and it's equal to 9. And remember, little a has to be on the right-hand side. It has to be opposite. So here's what that would look like right there. Little a is equal to 3. And again, what I want you to notice is there is no triangle. And even if you tried to draw it on the other side, even if you tried to draw it on this side, no triangle. Finally, this last one. Now notice I didn't change these. These are way too big. So for this one, if you haven't already, do on a separate piece of paper. So when you've done that, here's our angle A, 62 degrees, which is kind of like that. Here's our little b, 15 centimeters. Again, 62 degrees. Now, again, when you physically do this, here's what you're going to get. You're going to get that triangle right there, and you're going to get this triangle right here. What you're going to get is two triangles. So again, you really need to do this. You really need to physically do it so you actually believe something before you rely on your math to really see it. So one of the things we have to be careful with is just this basic idea of how do you determine if there is an ambiguous case. So the best way is to draw a picture and to imagine a right triangle. So basically, we didn't do that above because I wanted you to actually physically draw the picture. And once we imagine a right triangle, we can figure out the height of that right triangle, and then we can decide if we have two answers, two triangles, or just one, or none, but we'll either have one or two. So here's a story. Maria and Carl are part of a team that is studying weather patterns. The team is about to launch a weather balloon. Maria's rope is 7.8 meters long and makes an angle of 36 degrees with the ground. Carl's rope is 5.9 meters long. Assuming that Martina and Carl form a triangle, what is the distance between the two? So let's have a look at this, a quick little picture over here. Okay, here's the ground, and here is Marina right here, and she has a rope that is 7.8 centimeters long, 7.8. So I'll label this A for Marina, and the rope forms an angle of 36 degrees to the ground. Now we're guaranteed to make a triangle, so what we really need to do is, okay, with Carl's rope of 5.9, if you actually physically did this right now, which you could always do, you would see that there can possibly be two. But here's another way to do the problem we did on the other page. What we can do is we can simply figure out, just like that solar panel example, we can figure out the height of this right triangle. And it's really easy to do. And if we know something about this height, then we have a way better idea of how many triangles we can actually make. So in this one right here, if we go ahead and figure this out, we know the sine of 36 is equal to h over 7.8. H is equal to 7.8 sine 36. And if we got out our calculator and we went 7.8 sine of 36 degrees, we get the height of that right triangle is about 4.6. So we'll just say about 4.6. So in order to make a right triangle, if Carl's rope was 4.6 meters long, we would only get that too. But again, here's what this is now saying. Saying that Carl's rope, I'll do it in green now, saying that Carl's rope is greater than 4.6, it's actually 1.3 meters long. If we imagine the ground, Carl's rope would go in the ground. But what we could always imagine, just like I had you do earlier, is imagine swinging that this way and imagine you swing it that way. And we do that. What I hope you see is there's two possible triangles. So right there, we know the answer, and hopefully pictorially, we know why there are two triangles. And now we're just going to go ahead and we're going to look at each case. So let's look at the first case, situation number one. And situation number one looks like this. Here's the ground. Here's Martina's rope, and I'm just going to imagine Carl being on the other side. So here's Martina, here's Carl, and there's the balloon. So right here we have 36 degrees. This is 7.8, and this is 5.9. Now, in this question right here, I do have a matching pair. So this is, again, we're doing the sine law. But I don't know angle B and I don't know angle C. And remember what I want to know. I want to know this. What is the distance between these two things? So in order to do this, what I really need to know is that right there. But I can't do that right away. In order to figure out angle C, the first thing I need to do is figure out angle B, and I should be able to do that with the sine law. So if we can figure out angle B, then we're going to know what angle C is, and as soon as we know what angle C is, then we can go ahead. So we're going to go ahead and find angle B, and again, in order to angle B, we have the sine law. Given that we want to find the angle, we're going to use this version of the sine law, where we always want to put the unknown on the top. And when we go ahead and do that, we'll have the sine of B over little b, which is 7.8, is equal to the sine of 36 over 5.9. And when we isolate B, sine of B, we're going to have this. So again, we're going to multiply this over. So all of this stuff is not new. This is the sine law stuff we've done over the last 2 units. What we end up with is sine of B is equal to 0.777. And when we go second sine to get the angle, we end up with angle B is 51. And if angle B is 51, angle C, interior angles of a triangle, is 93 degrees. So all of that work, which is important work, to get angle C, now what we can do is we can figure out little c. So little c over the sine of 93 is equal to little a over the sine of 36. And when we do our algebra, we get c is equal to 5.9 sine 93 divided by sine of 36. And we push all those buttons on our calculator, and we get 10. So they are standing 10 meters apart. Now remember, angle C is the biggest angle, therefore little c is the biggest side, and that's looking pretty good. So there's our first situation where we swung the 5.9 over this way. Well, the other situation is swinging the 5.9 on this side. So that's what we're going to do now. We're going to do situation number 2, triangle number 2. So situation number 2 would look like this. Here's the 36 degrees. Here's Martina. Here's Carl. Here's the balloon. 7.8, 5.9. Again, we do have our matching pair, but just as before, we want to find little c, so we need to find this, but just as before, well, this is what we have to find first. So in order to find this, we're going to do exactly this. We're going to do exactly the same. We're going to go sine of b over little b is equal to sine of a over little a. So the sine of b over 7.8 is equal to the sine of 36 over 5.9. And we're going to go ahead and solve that exactly the same way. And we're going to get sine b is equal to 0.777. and angle B is equal to 51 degrees. This is the only answer our calculator can give us. But here's what we know from our picture. But we know angle B has to be greater than 90 degrees. So again, angles on the line. So angle B has to equal 180 minus 51, which equals 129. And if angle B equals 129 and the other angle A is 36, then angle C has to equal 15 degrees. And this is the one we want. So we're going to use that information now and figure out little c. So little c over the sine of big C is equal to little a over the sine of big A. And we'll do our algebra, multiply the sine over, and then we'll punch everything in our calculator. And when we do that, we get 2.6. So lots of calculations, but they're all old. So here's a summary, and I'm not going to go through it. I want you to read this, but this is basically what we just did. A nice little summary. And this is a really good thing to have right beside you as you're doing this unit and as you're reviewing. And again, it's a physical example of what happens when. But I can't emphasize enough, the most important thing from today is draw yourself a picture.